All right, hi everyone. I'm gonna continue our Exomoon discussion. My name is Mikayla Wilson. I'm a fourth year grad student at UC Santa Cruz, where I work with Andy Skemmer and Marianne Limbach. And it seems to me that the topic of exomoons is particularly fitting for this week's theme. On one end of our problem, we have an idea that the satellite formation theory tells us moon should be a common outcome of planet formation. And at the same time, we've gotten the opportunity to really do in-depth studies of the moons within our own solar system, but we have yet to kind of extend this understanding out into the rest of the universe. There has still not been a confirmed exomoon detection. And on the other end of things, the exoplanet end of things, we are really trying to push down into the smallest regimes. And so JWST kind of puts us in this wonderful position to hopefully bridge the gap that's left observationally by exomoons and exosatellites. So there are a lot of ways to try and search for these exomoons. As we just heard, microlensing can be a really exciting one to think about. And I'm going to talk about transiting exomoons today. So an important note here is that rather than thinking about how a planet's transit would change depending on the presence of an exomoon, instead we are considering the moon's transit within the host planet's light curve. And so I'm going to walk us through a case study where we use this method to search for transiting exomoons around WISO 855. So WISO 855 is a free-floating planetary mass object. So it is between 3 to 10 Jupiter masses. And because it's free-floating, that means that there's no host star that's going to kind of drown out the signal of an exomoon transit. It is the coldest of the known Y dwarfs. And the reason that it was discovered in the first place, even though it's so faint, is because it is really nearby at about 2.3 parsecs. And so in terms of observations, we have 11 hours of time series spectroscopy with JWST near spec. And something that we're going to use to our advantage is the fact that the light curve information we have is spectrally resolved. So like I said, this object is very cold, and so there are expected to be clouds. There's different things going on with the chemistry, and that variability might look different at different wavelengths. But in exomoon transit, we would expect to not be dependent on wavelength. It would be all of the light being decreasing, or all of the light decreasing since it's being physically blocked out. And so we've chosen two different wavelength regions with kind of different variability patterns, and we can build our light curves from these. So this is what they look like. And we fit our Gaussian process models to these light curve. So the first one is going to be a GP plus transit. And what we assume is that if there's something that looks like an exomoon transit, it needs to be at the same time in both light curves. And so that kind of helps us break the degeneracies a little bit. And then we also have our GP only model. So we're not assuming a transit, and any sort of bumps and wiggles in this light curve are going to be attributed to the host variability. And so what's spit out is this log z value. You can just think about this as how confident we are in a model. And the model with the greater log z is going to be the favored model, where the difference between them, the delta log z, is how favored a model is compared to the other one. So something close to 0 is going to be not worth mention, while 4.6 or greater would be decisive confidence that a model is preferred. So just a note here, like I said, there's lots of bumps and wiggles in this light curve. There could be features of the host variability that look like exomoon transits. And so we kind of do a correction to make sure that we are correcting for the extent to which the host variability is looking like transits. I'm not going to go into the details here, but happy to talk about that in the future. And so I'm going to cut to the chase. For WISO 855, we found a delta log z that was in the not worth mention range. So we don't think that there is an exomoon present in this data set. And I'm okay with that. And the reason is because it's actually not super probable that there would have been an exomoon in this data set. And that's going to kind of be shown here in this figure. So this is the probability that we would have caught a transit as a function of separation. And so this is taking two things into account. One, that the inclination of WISO 855 is unknown. So maybe we do have moons that are going around WISE-855, but if instead of transiting, they're going this way, we never would have been able to detect them. And then also that we are using an 11-hour observation. So maybe there are moons going around, but we happen to look at them while they were over here rather than passing in front. And so this kind of just shows our Galilean moons for reference. So if we were thinking about an Io-like separation, we would have had a 6 to 15% chance of catching a transit in this data. And so this is just for one object, but of course that's just going to improve as we continue to look at more and more observations. And so if we think about similar observations, we would have a 95% chance of catching a transiting exomoon after 18 sort of observations like this one. So also with an unknown inclination, 11-hour observation. And so whether or not there's a transit in the data is not necessarily going to guarantee that we'll see it. So we have to test the performance of our models. So this is some injection and recovery tests that we've done for this work. I have 6 different transit depths, and for each of them, I had 50 random injections to see how well we were able to recover them. And this is an example here. So we injected a 50-minute transit of 0.3% at about 4 hours. And you can see the GP does a pretty good job at sort of identifying the host variability. And when we subtract it off, we see the shape of the transit there. And just to take us back to our delta log Z idea, this was decisive confidence that the GP plus transit model was favored over the GP only model. So this plot just kind of summarizes these tests. And as you can see, as we go to smaller and smaller transit depths, of course, our recovery is dropping off, which makes sense. I also have here Io and Titan mass analogs and where that would fall in terms of our transit depths. And so if we consider our 0.5 and 1% transit depths, that was going to be a 96% recovery rate. So kind of combining these two ideas, whether or not we'd be able to find a exomoon in the data and how well our models are doing, this is going to tell us that we'd have a sort of 91% chance of detecting a Titan mass analog exomoon after we observe 11 WISE-855-like objects. And so, like I said, this is going to be assuming that we have 11-hour observations, that we don't know the inclination, but that probability will just increase if we are looking at things that we know to be edge on, or if we look longer at these objects. And so I'm just going to leave my takeaways here. I do want to note that 18 is not necessarily a crazy number. It's not 100. And so we have existing data sets that we're able to sort of repeat this method on, and incoming data sets as well. Thank you. I'd be happy to take questions.
Great, plenty of time for questions.
Hi, thanks for the great talk, Eric Van Klepper from the University of Chicago. I'm curious from like a formation history standpoint, how different a moon around a Y dwarf is from like a planet around an M dwarf.
Yeah. Thank you for this question. Yeah, I do get this question often because, you know, we're talking about a free-floating planet. I called it a planetary mass object, kind of to be more careful about that. And so, yes, in terms of the free-floating planet population, we would expect these to be things that formed like brown dwarfs, failed stars, but also it could include objects that were ejected from different systems. And some models show us that there is a high chance, around, I think 85%, that our moons can stay attached to the planet as it's ejected. And so even if we are considering the sort of brown dwarf formation idea, there's still the chance that the satellites would be representative of the exomoon population in general, especially because these sorts of objects are going to be most similar in composition, mass, spectral type to the sorts of planets that we are directly imaging right now.
Up here. Thank you.
Hello, this is Bryce Bullen from Eureka Scientific. So, on that note, could you have any irregular satellites survive ejection?
That's a good question. I am not sure about irregular satellites in general. I think it might be similar to the regular ones. I think the important note is that they could stay bound to the planet if it's ejected, but that doesn't necessarily mean that they're going to be at the same sort of inclination. So that's kind of maybe the more pressing thing to think about, because if we're looking for objects that we know are close to edge on, but maybe the moon is orbiting around the pole at that point if it was ejected, then that would be the thing to consider here. Thank you.
Great. All right, well, with that, let's thank Mikayla again.
Thank you.